Okay, we did order of reaction. Order of reaction, as I said, it is represented by the small letter n. Suppose we if A moles of A plus B moles of B is giving C moles of C plus D moles of D, and its rate law is going to be K into molar concentration of A raised to X and B raised to Y, where X and Y, I said, they are the experimental values which we get from the experimental data. So if I'm writing the order of reaction, then we just saw that order is going to be the sum of powers, that is X plus Y. Now let's solve some simple numericals or simple questions which can be solved, which can be asked on the order of reaction. So the numericals are like, if I'm saying, suppose there is a reaction 3 moles of A plus 2 moles of B gives 2 moles of C plus 3D. And the question is, rate is given, the rate law, that is K into molar concentration of A raised to 3 by 2 and B raised to 1 by 2. The question can be asked that what will be the rate law of this reaction, what will be the order of this reaction. So we have to calculate the order. Since the rate law is given, so we have powers also, that means the X value is 3 by 2 and Y value is 1 by 2. So simply we have to find out we have to calculate the sum of these two powers, and which will give us the order of reaction. So here I can say order is equal to 3 by 2 plus 1 by 2, which is going to be 2 by 2, 2 by 2, 4 by 2, 4 by 2, that is, answer is going to be 2. So I can say that here the reaction is a second order reaction. So this type of question may be asked. Here the order of reaction for each particular reactant is fractional, but when I'm calculating the overall order of reaction, then overall order reaction is integer. Then second, suppose there is a reaction like 2 moles of A plus 3 moles of B gives 4C plus 2D. This is the reaction, and its rate law is given as rate is equal to K into molar concentration of A raised to 2 and B raised to 1. The question is what will happen, what will be the new rate of reaction when the concentration of A is doubled and B is halved. So question is, what will happen if A is doubled and B is halved. So if concentration of A is doubled and B is halved. So now let's see what will happen. Since I am changing the concentration, so the rate of reaction will ultimately change. So instead of rate, I am just writing rate dash here. So rate dash is equal to, it is given that A is doubled, so it is K into molar concentration of 2A whole square, and B is halved, so it is going to be half of B. Here we can write 2 will come outside, so we'll get K, 2 will come outside as a 4, and from here it will be 1 by 2, and the remaining things are K into molar concentration of A square into B. This will get cancelled, and ultimately I will get 2 moles of K into A square into B. That means this K into A square into B is nothing but the rate, initial rate. So I can say that when A is doubled and B is half, the new rate of reaction is twice of the original rate of reaction. Or sometimes they also ask a question, what will be the ratio of the new rate to the original rate. So if they are asking a ratio then I can say new rate to original rate, that is rate dash upon rate. Answer is going to be 2. So such type of questions are asked on the basis of the order of reactions. Now let's talk about something about the zero order reaction in detail. So zero order reaction, zero order reaction. First, what is zero order reaction? Then zero order reaction means a reaction whose rate does not depend on the concentration of reactant. For example, last time we did the example 2 moles of ammonia gives N2 plus 3H2. if I'm writing its rate law, then rate is equal to K into molar concentration of ammonia raised to 0. When we perform experiment, from the experiment we get data, and from the data we come to know that the power is 0 here. That is, rate is equal to K into ammonia raised to 0, and anything raised to 0 is 1. So here I can say that rate is equal to K. It means in a rate law there is a no reactant concentration. Means simply I can say that the rate of reaction is independent of the concentration of reactant. It does not depend on the concentration of reactant, and such reactions are called as zero order reaction. When I am saying that rate of reaction does not depend on initial concentration, that it means what? See, generally what happen, as suppose if I am taking 100 grams of reactant, some reactant which is 100 gram initially. After 15 minutes, as the time it will increase, the reactant concentration will goes on decreasing. So after 15 minutes, suppose it becomes 90 gram. Means in first 15 minutes, the amount decreases to 19 gram. We learn in the same chapter that the rate of reaction depends upon the concentration of reactant. It means as the reactant concentration goes on decreasing, the rate of reaction should also decrease. But in case of zero order reaction, such thing does not happen. In this case, the rate of reaction remains constant. It does not changes with the reactant concentration. It means with the time, the rate of reaction will remain same. It will not change. So if in first 15 minutes the reactant consumed is 10 grams, so in next 15 minutes also the reactant consumed is going to be 10 gram only. In next 15 minutes again the reactant consumed is going to be 10 gram. That means the left amount is going to be 70 gram. Means here I can say that the rate of reaction does not changes with the change in the concentration of reactant. Now the question arises that why the reaction does not depends upon the concentration of reactant. So in this case, the reaction takes place in the presence of platinum, which is acting as a catalyst. Let's see why the reaction is independent of the concentration of reactant. For example, suppose this I have a container. This container is full of ammonia gases. So full of ammonia gas. There is a platinum metal which is acting as a catalyst. Now during reaction, what happens? Whatever the ammonia we are having, all the ammonia get absorbed on the surface of platinum. All the ammonia means all the reactant molecules get absorbed on the surface of platinum metal, and when ammonia get absorbed on the surface, they react or they decompose, they produces nitrogen and hydrogen, and finally they leave the surface. It means, in simple word, I can say the reactants are getting absorbed on the surface, and then once they form a product, they leave the surface. So continuously this process is going on. At a given time, I can say the number of ammonia molecules which are getting absorbed on the surface is very less or very small compared to the total number of ammonia molecule which is present in a container. That means a very small fraction of ammonia is getting absorbed. Now suppose if I am adding small amount of more ammonia. If I am adding a small amount of more ammonia, what do you think? Is it going to increase the rate of reaction? Then simply answer is no. The rate of reaction will not increase because already the ammonia molecules are in a large quantity inside the container. So if I am adding a small amount of ammonia, the reaction will not increase because the rate of reaction depends, in this case the rate of reaction depends on the amount of ammonia which is getting absorbed on the surface, and after the addition of this ammonia also the amount of ammonia absorbed is going to be same. So here instead of the ammonia concentration, the rate of reaction depends upon the surface area of platinum. If I am increasing the surface area of platinum, ultimately more number of ammonia will absorb, and more number of ammonia means the rate of reaction will increase. So here in this case I can say the rate of reaction does not depend upon the concentration of reactant, that is ammonia. Instead it depends upon the surface area which is provided by the solid catalyst. So I can say all those reactions in which the reaction takes place on the solid catalyst are considered as a zero order reaction, because in all those reactions the rate of reaction is independent of the rate of reaction. Now for zero order reaction in which the rate of reaction is independent of rate of reaction. In this case, now let us derive a formula for calculating the rate constant for a given reaction. Suppose I am considering a reaction So consider a zero order reaction. A gives product. So as I said, it is a zero order reaction, so its a rate law is going to be rate is equal to K into molar concentration of A raised to 0. Since zero order reaction, so power is going to be 0. Therefore, in next step, we can say that rate is equal to K. That is, the rate is independent of the rate of reaction. At the same time, we can write its instantaneous rate also. Instantaneous rate only in terms of reactant, that is, it is going to be minus dA by dt. So from 1 and 2, we can say that minus dA by dt is equal to K into, okay, it's a K. Let us shift this dt and minus sign on the right hand side, so we will get dA is equal to minus K into dt. Now whatever the terms we are having, it is in a differential form, but we want the formula for the whole equation. So let us remove this differential form by integrating. So integrating this equation. So if I am integrating it, it is going to be dA is equal to K is a constant and then integration of dt. Now here let us integrate in a limit of concentration, means let's fix the upper limit and lower limit. For concentration, the lower limit is A0 and the upper limit is AT, and here it is 0 to T. Now what is A0 and AT? Let's see. A0, it is nothing but the concentration of the reactant when the time is 0. It means I can say this is nothing but initial concentration of reactant. What is AT? AT is a concentration of reactant after time t, means when the time is t. That time may be 10 minutes, it may be 15 minutes, maybe 20 minutes. If I am saying t is at 20 minutes, then AT is going to be the concentration of reactant after 20 minutes. If I am saying it's at 25 minutes, then AT is going to be the concentration of reactant after 25 minutes. So let us integrate it. The integration of dA is A, so it is going to be A. The lower limit is A0 and AT is equal to minus K. The similarly for time, dt is t, 0 to t. Therefore, in next step we can write AT minus A0 is equal to minus K into t minus 0, that is t. Let us shift minus sign on this side, therefore it will become, this AT will become minus and A0 will become plus. So we will have A0 minus AT is equal to K into T. We are deriving a formula for K for zero order reaction. So K is equal to, we will have A0 minus AT upon T. So we got this formula for a zero order reaction, that K is equal to A0 minus AT upon T. What is A0 here? Then simply A0, it is a initial concentration of reactant, that is the reactant which is taken in the beginning. AT, it is a concentration of reactant after time t, and T is a time. But obviously AT is always going to be smaller than A0, so your answer is always going to be positive for the rate constant. So we got a formula for the zero order reaction for the K. Now the next is, let's talk about the half-life period of zero order reaction. So half-life period, that is T half. It is represented by T half. Now first, what is half-life period? Then half-life period, I can say that it is the time needed for a reactant concentration to reduce to half of its initial amount. It's the time needed for a reactant to reduce to half of its initial amount. It means, suppose if I am taking a 50 grams of reactant in the beginning, then we know that with the time the amount of reactant will goes on decreasing. So slowly from 50 gram it will become 40, 30, 25. 25 means it becomes half. So the time which is needed for a 50 gram reactant to reduce to half, that is 25 gram, will be considered as a half-life period. So suppose from 50 to 25 it takes 30 minutes, then half-life period will be considered as a 30 minutes. So here we have to derive a formula for the half-life period of zero order reaction. So for zero order reaction, we just derive a formula K is equal to, let's start with this formula. K is equal to A naught minus AT upon T. We are talking about the half-life period. So after a half-life period, so let's talk about the condition after a half-life period. Once I'm saying after a half-life period means one half-life is over. So how much time is completed? One half-life. So T will become T half. Now after a half-life, AT, what is AT? AT is the amount of reactant left after time T. That is AT now, it's a half-life. So AT will be what? It is the amount of reactant left after a half-life. So how much reactant will left after the completion of one half-life? So half of initial. That is initial amount is A naught upon T. Let us substitute both the terms in this formula. K is equal to this. So here we will have K is equal to A naught minus AT. Instead of AT, we can write A naught upon 2 upon, instead of T, I can write T half. Therefore, I can say K is equal to 2 A naught minus A naught upon 2 T half. Therefore, I can say T half is equal to, we will have 2 A naught minus A naught means A naught upon 2K. So we got this formula for half-life period. From this formula, I can say that T half is directly proportional to initial concentration of reactant. Again, important point. That for a zero order reaction, the half-life period depends on the initial concentration. It means, suppose if I am taking 100 grams of reactant, and if its half-life is 15 minutes, means if it's getting reduced to 50 gram. But if I'm changing the initial amount, suppose instead of 100 gram, if I took 500 grams of reactant, then this half-life period time also changes. Instead of 15, it will become 75 minutes now. To reduce to half amount, that is 250 grams. So if you are changing the initial amount, ultimately the half-life period will also change. And that's why we are saying that half-life period is directly proportional to the initial concentration of reactant, that is A naught. So this is a half-life period. So for a half-life period, we got a formula T half is equal to A0 upon 2K. Now let's see some example on the half-life period. Suppose I am taking in the beginning 100 grams of reactant. 100 gram of reactant. After a particular half-life period, I can say that it will reduce to 50 grams. Now the question is, what will be the reactant after next half-life period? Generally, if the reaction is a first order reaction, suppose if it is a first order reaction, then in case of first order reaction, what happened from 50, it again reduces to half, means it becomes 25 grams. Again, after half-life period, it becomes, again still reduces to half, that is, it from 25, it becomes 12.5 grams. But when it is a zero order reaction, after first half-life, it becomes 50 gram, and after next half-life, it becomes 0 gram. Question arises that why it reduces directly to 0. So simple, the answer is zero order. In case of zero order reaction, the rate of reaction remains constant. It means in the first half-life period, whatever the amount of reactant is going to be consumed, equal amount of reactant will consume in the next half-life. For example, suppose if here the half-life period is 30 minutes. So if in case of zero order reaction, the rate of reaction is same throughout the course of reaction rate is same. So if in first 30 minutes the reactant consumed is 50 minutes, then in next 30 minutes again the reactant consumed is going to be 30 minutes. So I can say that in case of zero order reaction, the full reaction get completed only in 2 half-life period. Once the 2 half-life period, the reaction is over if it is zero order reaction. So after the 2 half-life period, the reaction is over. So here I can say from 100, thus if this is 100, so after a half-life period it will become 50, and from 50 it will reduces to 0, and this is equal to nothing but the total. This is T half T half, and this is total lifetime. Total lifetime, it means the time required for the complete reactant time required for the completion of reaction. So time required for the completion of reaction, I can say, is equivalent to the 2 half-life period. We can prove also the same thing, that is time required for completion is 2 half-life. Let's see how. We have again a same formula, K is equal to A0 minus AT upon T. Now I'm talking about the total lifetime period. Total lifetime period means the reaction is completed. So T is equal to, I can say, TLT, that is lifetime. If the lifetime is over, means the amount of reactant left is equal to, amount of reactant left will be equal to 0 molar. So amount of reactant left will be equal to 0 molar. The reason, because the reaction is completed. Reaction is completed means there is no reactant left. So from this, let us substitute both the things in the formula. So K is equal to A naught minus AT is what, 0 upon T lifetime. So here I can say T lifetime is equal to A naught upon LT. K. We have T half and we have this lifetime. Let us divide both. So I can say lifetime, this is the formula for the lifetime of the zero order reaction, upon T half is equal to, for lifetime it is A0 upon K, upon half-life period is A0 upon 2K. A0 will get cancelled, K will get cancelled. This is 1 upon 2. That means I can say lifetime upon T half is equal to 2. It means it is equal to twice of half-life period. So I can say that for a zero order reaction, the total time required for the completion is twice of half-life period. So if there is any question like half-life period for the zero order reaction is 15 minutes, then time required for the completion of reaction, then answer is going to be 100 minutes. That is the double of half-life period. Now the next is a graph for the zero order reaction. In this chapter, we are having a certain graphs, and those graphs are very important from the entrance exams, because many times it has been observed that the questions are asked on graph only. So we are having two graphs for the zero order reaction. With the help of graph also, we can decide whether the reaction is a zero order, first order, second order, or third order. That is on the basis of the nature of a graph. So here we have the first graph. It is for the zero order reaction. It is a rate graph of rate versus concentration of reactant. Now rate versus concentration of reactant, that is AT. So we have for zero order reaction, I can say that rate is independent of concentration of reactant. That is, rate is equal to K into molar concentration of A2 raised to 0. That means I can say rate is constant, that is K. Rate is constant means you increase or decrease the rate of reaction. It is you increase or decrease the concentration of reactant, but the rate of reaction is going to be same, means it will not change. So if I'm plotting a graph, it's a rate versus concentration of reactant, that is AT. When a graph is plotted in this case, here I can say rate is a constant, means if I'm increasing a concentration of reactant or if I'm decreasing a concentration of the reactant, the rate of reaction is going to be same. If the rate of reaction starting from here, it is going to be same throughout the course of reaction. It will not change. So suppose after performing an experiment, I collected data of the rate versus AT, and from this data, if I'm plotting a graph, and if the graph nature is like this, then I can say that that particular reaction is a zero order reaction. The another graph which we have is a graph of AT versus time. Now I wanted to know the graph, the nature of a graph of AT versus time. So for simply, if you wanted to know the nature, then I will simply say that find out the formula in which AT and times both comes together. So we have a formula in which AT and T comes together, and the formula is K is equal to A0 minus AT upon time, which is related to the zero order only. Now try to convert this formula in the form of y is equal to mx plus c, because if we convert this formula into the form of y is equal to mx plus c, then everything will be known to us, that is the nature of graph, about the slope, about the y-intercept, everything we will get. So just write the term which is going to be on y-axis, it should be on the left hand side, and this is going to be the x-axis term. Here for me, this is a y-axis term and this is on x-axis. So y-axis term is 80, so 80 should be on the left hand side, and this t and 80, that is y term and x term, both should be on the opposite side. So I'm transferring this t, so it is kt is equal to a0 minus 80. So here the 80 is the term which is on y-axis. The term which is on y-axis and the x-axis, they should be positive. So to make it positive, shift it. So we will get 80 is equal to a0. The y and x both term cannot be on the same side. So if I'm shifting 80 on the left hand side, then kt, it is on the right hand side. So it will ultimately become minus kt. Now the 80 which is on the y-axis is positive. What about the here? This is negative. But here we will consider that negative is k, not the time. Time is positive and this negative sign is because of k. So if I'm comparing it with y is equal to mx plus c, then here I can say that this is on y-axis, that is this is the value of y, this is the value of x, means the graph is going to be y versus x-axis, that means concentration of reactant AT versus it is going to be time. Since the equation is, this main equation is like a y is equal to mx plus c, so the nature of a graph is going to be a straight line, and plus this is the value of m which is a minus k, that is a slope is negative, and slope is negative means the straight line is going to be from top to bottom. And here we have the value of c also. C, it is a y-intercept, so a naught is going to be y-intercept. So the graph is something like this, straight line from top to bottom, and the point where it will cut the y-axis will be a naught. So this is the graph. The slope is minus k, and the point where it is cutting the graph, this y-axis is a naught. And we can say this is going to be a naught because this is 80, and if the time is 0, then 80 will become a naught, that is its initial concentration. So if I have the two data, that is a concentration of reactant left after time t, that is the time and the concentration of reactant. So if I am plotting both, with the help of these two data, if I am plotting a graph, and if the nature of graph is something like this, then I can say that the reaction is going to be zero order reaction. Okay. So these are the two graphs. If it is a rate versus AT, the graph is going to be a straight line, and if it is a AT versus time, it is in a straight line from top to bottom. Now let's talk about the certain reactions which are considered to be zero order, and they are asked in exam. So certain example of zero order reaction. The first one, photochemical reaction. Whatever photochemical reactions we are having, all those photochemical reactions are considered as a zero order reaction. The example is H2 plus Cl2 gives 2HCl. The reaction takes place in the presence of sunlight, that is H nu. H nu is the energy associated with the photon. So H2 plus Cl2 gives HCl. This is the photochemical reaction. The rate of photochemical reaction does not depend upon the concentration of reactant. Means if I am writing here the rate law, then I will say rate is equal to K into molar concentration of H2 raised to 0 as well as Cl2 raised to 0. Means the rate is independent of the initial concentration of reactant. Instead, here the rate of reaction depends upon the intensity of light. Photochemical reaction means where a light is needed to carry out the reaction. So here the rate of reaction depends on the intensity of light. Intensity of light, that is the number of photons falling on the reactant in a per unit time on a per unit area. So here I can say the first one, so whatever the photochemical reactions we are having in the exam, if they are asking about the order of reaction and if there is a photochemical reaction, then answer is going to be 0 order. The second reactions which are considered as a 0 order is enzyme catalyzed reaction. Enzyme catalyzed reactions are again considered as a 0 order reaction. If there is any reaction in which the enzyme is used as a catalyst, then that reaction is also considered as 0 order reaction. The third, reaction taking place on the surface of solid catalyst. Reaction taking place on the surface of a solid catalyst. Solid catalyst, example I can say we just did, that is 2 moles of ammonia gives N2 plus 3H2. The reaction takes place on the surface of platinum, so it is going to be a 0 order reaction. Another example I can say 2 moles of N2O gives 2 moles of N2 plus O2. The reaction again takes place on the surface of catalyst, that is platinum. So again it is also going to be a 0 order reaction. So these are the examples of 0 order reactions. If any such type of reactions are in the exam, just consider that they are 0 order reactions.